So like I was saying, when we are working with a power series, which represents a function, right, just a different formula for a function we already know, the coefficients of that power series have to be recording the derivatives of the function that I'm interested in. Just like we were interested in the partial sums for an arbitrary series when we were working last week, we're going to be interested in partial summation for Taylor series as well. But that just means that I've got a polynomial. And not just a polynomial with a very specific formula. So I have some function that I've already picked out. I'm calling it f of x. I want to make sure that f of x has derivatives of every order. So f of x exists, f prime of x exists, f double prime of x exists. I can continue to take derivatives as many times as I like, and I will never be stopped by discontinuity or anything like that. Well, if I have a function like that, then I can construct this kind of polynomial. What do I mean by construct? I can at least tell you what its coefficients are going to be. The coefficients of this polynomial are exactly what I get from calculating the higher derivatives of the function that I care about. So I'll take my first derivative, divide by 1 factorial, multiply by x minus a. I'll take my second derivative, divide by 2 factorial, multiply by x minus a squared, and so on. And eventually, I'm going to stop. I'm going to stop, say, at the nth derivative, which means I will be dividing by n factorial, and it means I'll be taking x minus a to the power n. All of those things, because I stopped, give me a polynomial. And again, this is the nth degree Taylor polynomial. Here, the f is the function that I used to find all of those coefficients, and the a is where I am centering that polynomial. So the question is, how close is this polynomial to the function that I care about? Maybe the function I've got is, almost a polynomial with, a little bit of a remainder, a little bit of an error term. Here are some of the Taylor polynomials for the exponential function. The first Taylor polynomial is degree 1, so it's just 1 plus x. The second degree the Taylor polynomial is a quadratic, so it's 1 plus x squared divided by 2. The third degree Taylor polynomial for the exponential function is 1 plus x squared on 2 factorial plus x cubed on 3 factorial, so a cubic. And here is a graph showing all of those polynomials at the same time. The higher degree polynomial we get, well, it looks like those polynomials are getting closer to the graph of the exponential function. They are very close at x equals 0. That's where we centered these polynomials. And they get farther away as we move away from that coordinate. So I would like to calculate the limit of these Taylor polynomials. But that's kind of saying that there should be some kind of error term that's going to 0. So what is this error term, this r sub n? It's going to be some other function. And we want to have a formula so that we can manipulate this remainder.